In the first video for this module, we are introduced to the concept of constructing a logical proof for an argument, and we saw the specific formal method that is traditionally used to do so. And of course, in constructing a logical proof, we rely fundamentally on a good number of rules of implication, that is, on various forms of arguments that we recognize as inherently valid. So far, we've only seen 4 such rules, and these 4 are really central rules, one that you'll be frequently using, but they are hardly the only rules that we have to use. Now, these original 4 include, of course, the modus ponens, the modus tollens, a pure hypothetical syllogism, and the disjunctive syllogism. At this point, what we're going to have to do is simply add here and keep on adding to our list of tools to use in constructing proofs. To that end, in this video, we'll be discussing the next 4 rules of implication that we'll need for this whole process. And unlike the first 4, which we've already seen and studied in the last module, we'll be looking at a couple of new ideas here. Before we start looking at these, I would like to suggest to you that in this module, and in terms of constructing proofs, it is ultimately not enough for you to simply memorize these different rules and then apply them. It is also very important that you understand why these rules work. Why, in other words, all of these forms are in fact valid forms of arguments. And the reason for this is that constructing a proof is not a simple mechanical process, but one rather that takes a good deal of strategy and creative thinking to make work. But if you do not understand the ends to which you're applying your strategy, this will make things rather difficult. To return to the chess analogy that I used in the last video, if you want to be any good at chess, it's not enough that you simply know the basic rules about how each piece moves and then you move them accordingly. You also need to understand the fundamental goals that you have in moving them and what value each piece has in the big picture for achieving this goal of a checkmate. And of course, much the same could be said of constructing a proof in logic, because in the end what we find is just knowing what the rules tell you isn't enough unless you understand what they're supposed to do, how to use them, and you can formulate basic strategies that make sense of what we're trying to accomplish. In any event, let's start walking through our next 4 rules. We can begin with the only one of the 4 that you've already been introduced to in this class, and that is a constructive dilemma. We'll abbreviate these in our justifications of the proofs with the letters CD so that we know what we're talking about. Now, as you should already know, a constructive dilemma is essentially just 2 modus ponens that have been weaved together by way of disjunctive propositions. The basic form of this type of argument would be so that the first premise is a set of conjoined conditional statements. That is, if P then Q and if R then S. The second premise will, following the rules of modus ponens, resolve each of these conditionals by affirming the antecedent and then connecting them together with a disjunction. That is, in the second premise, we get essentially it's either P or it is R. And then the conclusion will resolve these arguments by affirming the consequence using the rules of modus ponens, and again connecting these together with the disjunction, so that we get either Q or S as our ultimate conclusion here. As I did in the last module, I'm going to assume that you understand this form of reasoning based on what we studied there. But what is important here is not merely to recognize the form, but also to understand that this is valid essentially by rules of modus ponens. In the end, essentially, we can tear this apart into 2 valid modus ponens and see exactly what kind of argument it is and why it works as it does. It's also worth noting that we will not have a formal rule for a destructive dilemma. And the reason for this is fairly straightforward. As Hurley proposes, the constructive dilemma is the only form of dilemma that will be included as a rule of inference. By the rule of transposition, which will be presented in a later section, 7.4, any argument that is a substitution instance of the destructive dilemma form can easily be converted into a substitution instance of a constructive dilemma. Destructive dilemma, therefore, is not needed as a rule of inference. The next rule of implication that we have to discuss is a new one for us. This is called simplification, and it deals with inferences that we can make when dealing with conjunctions, that is, and claims. The abbreviation we're going to use for this in our proofs is simply SIMP, S-I-M-P. The basic rule of a simplification is this. If there is a line in the proof that has the form of P and Q, whatever P and Q stand for, then one is logically entitled to infer from this conjunct of the two terms that either term alone must be true. This means that we know from a conjunction of P and Q that P by itself must be true, and also that Q by itself must be true. So if we have a premise P and Q, or a statement in our proof that we know to be true, whether it's a premise or an implication, from this I can logically infer that the individual conjuncts that it's made up of must be true. So if I have P and Q, I can also necessarily say that P by itself is true. And of course, this goes both ways. If I have P and Q, I can also say that the second term Q is true. As a sort of quick aside, this rule is also sometimes called ampersand out, and it is called this because it allows us to pull out individual terms from a conjunction and then include these in our proof as new inferences. Now we might stop at this point to wonder why this follows and follows necessarily. And this is perhaps best answered by looking at our truth tables. If you recall, in the generic truth table for a conjunction, the only possible way that a conjunction can be true is if both of the conjuncts are true. And again, that's regardless of whether or not the conjuncts are simple or complex statements. Whatever they are, they both must be true for a conjunction to be true. And remember, in constructing our proofs, we are always going to begin with the presumption that all of our premises are true. And so, assuming we are using our rules of implication correctly, any inference that we draw distinct from the original premises must also be true. So we're going to assume the truth of these propositions. And so, of course, if you find a conjunction as one of your lines in the proof, then the only way that our presumption that the statements must be true could follow is if each individual conjunct in that statement is true as well. And so we now know that, of course, we get this as a necessary conclusion. The next rule we have also deals with conjunctions, that is, and claims, and can be thought of as sort of the opposite of the simplification rule. Now this rule is rather aptly named just conjunction, and the abbreviation we're going to use is simply CONJ. Now this rule essentially tells us that if there are any two lines in our proof that have been established as true, so they're either an original premise that we've assumed to be true, or a legitimate inference from these premises or other inferences by way of the rules we've been using, these can be put together into a conjunction of those specific terms. Now, to state this formally, if we find in our first premise here that P is true, and then we find that Q is also true in a second premise, then it necessarily follows that in conjunction of these two terms, whatever P and Q stand for, whether they're simple or complex propositions, this conjunction P and Q must be true as well. And this rather obviously, and I think very intuitively, follows from the basic truth table of a conjunction as well. Since once again we know that for a conjunction to be true, it is necessary that both of our conjuncts are true, then this means that any two true propositions, regardless of what they are, can be crammed together into a single conjunction and will remain true. This rule is also sometimes called the ampersand in, for the simple reason that it allows us to put individual propositions together into a conjunction. So whereas simplification takes apart conjunctions, conjunction works by putting things together into a conjunction. Now the last rule of implication that we have to work with deals with disjunctive propositions, that is with either or claims. And this rule is called addition, and it's abbreviated in our proofs with the simple ADD, ADD. This rule basically tells us that if we have a line available, call it P, whatever P stands for, then we are entitled to write down the disjunction of P with any possible proposition Q so that we can produce the disjunction of P or Q. Now, formally stated, this says that if our proposition in our proof P is true, whatever it is that P stands for, then we can combine this into a disjunction P or Q and infer that this is necessarily true. And again, it really doesn't matter what Q stands for, this proposition would have to be true. And we can see why this rule works once again by appealing to the truth table for our disjunctive operator. Remember that our objective in this proof is to justify the claim that every proposition in it is true. And interestingly, all it takes to show that a disjunction is true is that one of the two terms is in fact true. It really doesn't matter if the other is true or false, all it takes is one. And so if we've already established that P is true in our proof somewhere, whether that is because it's a premise that we've assumed already to be true, or it is some inference that was used to show that it is necessarily true by following the rules of inference, then this has to be enough to guarantee that any disjunction that is connected to P would have to be true. And that really, again, doesn't matter if Q is true or false, the disjunction would have to be true. Now, this rule is sometimes also rather informally called the wedge in, since it allows us to stick in any single term that has been established into our proof as a disjunction with any other possible term. So at this point, let's take a look at a couple of examples of argument proofs that will use some of these new rules for us. And I'll start with a fairly easy one. We can look at a more challenging one next. So in this particular argument, premise 1 tells us that A is true. Premise 2 tells us that B is true. And then premise 3 is a conditional statement that says, if A and B are true, then C would have to be true. And our conclusion that's drawn is it's either C or it is D. So our first step in this is to simply label all of the premises. We only have 3 in this case, so they get in order 1, 2, and 3. And then we want to set the conclusion, which is C or D, off to the side, separated from the final premise with a slash. As you will notice, we do not find our conclusion C or D anywhere in the premises of the argument. And remember, this is always a good starting point, to go look for your conclusion hiding out somewhere in the premises, as this will typically suggest a place to start. Now, we don't find C or D, but we do find C, and so this is probably a pretty good starting point for us anyway. Now, notice if we want to try to prove C is true, then we can do this by way of a modus ponens if we only can prove A and B is true. And so the first and most obvious step in all of this is to simply put together A and B into a conjunction by way of the first two premises. So if premise 1 says A is true and premise 2 says B is true, it follows by the rule of conjunction and necessarily that the proposition A and B would have to be true. So notice here we have in fact established that the antecedent of the third premise, if A and B are true, then C is true, that A and B is in fact correct. And if we know that the antecedent is true, then by rules of modus ponens, this necessarily proves that the consequent, which in this case is C, must be true as well. Now notice that our conclusion is it's either C or it is D. And again, we don't find that anywhere explicitly given in the premises, but we do find in line 5 that we know C must be true. And so by using the rule of addition, we can literally stick it together with any proposition, and that can be D in this case, in order to make a true proposition. So if C is true, then necessarily, and by the rules of addition, we also know that C or D is true. And of course, that's exactly what we're looking for. We have now shown that this argument must be valid. Let's take a look at a second example, and this one's going to be a bit more challenging. In this argument, we have in the first premise the proposition that if P or Q is true, then not R is true. In the second premise, we get P and T. The third premise says R or not S. The fourth premise says if U, then not S. And then finally in our conclusion, we get not U. Now, the first step, of course, is to set it up formally by numbering in order each of these individual premises, and then setting off to the right-hand side, divided by a slash, the conclusion, which is in this case not U. Now remember, a good and smart starting point here is to go see if you can find your conclusion somewhere in your various premises. And in this case, since the conclusion is not U, and we find U, that term in line 4, which is a conditional statement, we discover pretty quickly here that what we're going to have to do is use a modus tollens to get there. But of course, if we want to establish the truth of a modus tollens here, we're going to have to show that S can't be true, or we need to establish not S. Now, of course, we do find not S in premise 3, but given that this is a disjunctive statement, we're not in a position to simply assert that not S must be true. In a disjunction, what we would have to do is first prove that the other term is not true, and then the other one would have to be true. So what we're going to have to do is show that R is not the case, that is, prove not R somehow, and then from this we can use the rule of a disjunctive syllogism to show that necessarily not S is true. And then this allows us to run through our modus tollens. And of course, if we look at line 1, which is a conditional statement, we discover that not R is hiding out in there, and so we want to somehow dig that out. Well, as a conditional statement, what we discover quite simply is that we could use the rule of modus ponens to prove that not R is true, but to do that, we have to somehow show that the proposition P or Q must be true. Now, of course, we don't have a proposition in this argument that tells us P or Q is true, but we do know that P is true, and that's given to us in this conjunction P and T. And so this is going to be the kind of lever that allows us to run through this entire proposition. And we can get there by using these new rules we've seen. Now, the first step in this then is to simply dig the letter P out of that conjunction. T isn't really doing any work for us at all in this anyway. And since we know that P and T are both true, in order to have a true conjunction, that means that P by itself must be true. And so we can take that out and set it off to the side, following the rules of simplification. Now notice, in order to get our modus ponens in line 1, what we needed was the claim that P or Q is true. And it turns out that if we know that P is true, which we get in line 5, we can, by using the rule of addition, simply stick on Q into a disjunct with P, and that too would have to be a true proposition. From here, we can just start running through the various reasonings that we use to get to this anyway. If we know that P or Q is true, which we got in line 6, then connecting that with line 1, which is a conditional statement, is going to prove to us that not R must be the case. And we're doing this simply by the rule of modus ponens. Now, of course, in line 7, we've proven that not R is the case. And if we take up line 3, which is a disjunctive statement, which is R or not S, what we can show by the rule of a disjunctive syllogism is that not S must be true. That can be affirmed by denying R, which we get in line 7. And so finally, we're in a position to get to our conclusion by way of a rule of modus tollens. Because notice what we get in line 4 is the conditional statement, if U is true, then S is true. And line 8, which we just proved, is that S can't be true, so we deny S, and that allows us to deny U by using the rule of modus tollens. That's what we're after. If I can finally, using all of this reasoning, prove to you that not U must be true, that means that all of the premises are true, and the conclusion is true. It follows necessarily from it. This makes it a valid argument. So the last step for this video is to talk about various strategies that we can glean from what we understand of these rules. So we can continue the strategies that we had in the last module, and we can just add to them another few. So the first new strategy, strategy 6, says if the conclusion contains a letter that appears in a conjunctive statement in the premises, then we should consider obtaining that letter via simplification. So if we look at this particular example, notice that our conclusion is simply P, and the only place that we see P in this entire argument is in line 1, which says P and not Q. And if you stop and think about this for a moment, lines 2 and 3 are basically irrelevant. We can actually prove this in a single step, and it's pretty simple. What we can do is simply simplify from line 1. If we have a conjunction P and not Q, then notice both P and not Q would have to be true statements, and that means that P has to be true, and we're pretty much done with this one. The second strategy is strategy 7. This says if the conclusion is a conjunctive statement, so it's an and claim, consider obtaining it via conjunction by first obtaining the individual conjuncts. So notice in this case we have not P and R as our conclusion, and then in our first premise it says not P and Q, the second one says R and S, and of course we can get to this conclusion by simply putting in the rules as follows. Notice first of all, line 3 we get not P by rule of simplification. We can take line 1 and just drop the Q part and just say not P must be true by rule of simplification. Line 4 will tell us that R is true, again, in this case, looking at 2, but again, by using the rule of simplification. If the proposition R and S is true, then we also know that R has to be true by itself. And then finally, notice again what we can do is take lines 3 and 4, which is not P, and 4 is R, and just put them together into a conjunction by using the rule of conjunction. The next strategy, strategy 8, is going to tell us that if the conclusion is a disjunctive statement, then we can obtain this basically in two different ways, either through a constructive dilemma or by the rule of addition. To make this point, we can return to the example we used earlier in this video. In this particular case, the first premise says A is true, the second premise says B is true, and the third premise says if A and B are true, then C is true. And from all of this, we can see pretty easily how we would get C, but of course what we need is a disjunction, and this is where we can turn to the rule of addition. So of course, as we saw earlier, if we take premise 1 and 2 and put them together by way of conjunction, we get A and B. And then we can take 4 and 3 and put these together to just draw the conclusion C by a rule of modus ponens. But of course, C by itself isn't what we're looking for. We want C or D, and that we can do by simply adding D straight to this by way of a disjunctive proposition. And of course, if C is true, then C or D would be true, and it really doesn't matter if D is true or false. The disjunctive proposition itself must be true. And so we got there by a rule of addition. And again, the rule says if you have an either or claim, start thinking either that you're going to use addition to do so, or you're going to need a constructive dilemma, because it too will usually end up in a conjunction or disjunction. So the last strategy we have to look at is strategy 9. This says if the conclusion contains a letter not found in the premises, addition must be used to introduce that letter somehow. The only way we can bring in a term that is not found anywhere in the premises is to do that by way of a disjunctive proposition and by using addition. And of course, we saw this already, this example in the last one here. Notice that in our premises, D doesn't show up anywhere. We have C or D, but there's no D in our premises. And the only way you could possibly get D in there is by way of a disjunction. You're going to have to add it, but you have to do so by making an either or claim with some term that is known to be true in the various inferences or in a premise above it. So that is an end to our rules of implications. What we're going to see at this point is that we have other things to consider in terms of rules. And so we'll start that in the next module. But for now, you should know inside and out all of your rules of implications. Try to memorize these and get really comfortable using them in constructing various proofs.